Morning. Welcome to Breaking Payment Points of Interaction, presented by Nir Valtman and Patrick Watson in Mandalay Bay, BCD. Before we begin, a few brief notes. Stop by the business hall located in Bayside AB during the day and for the welcome reception from 5:30 to 7 p.m. tonight. The Black Hat Arsenal is on in the Palm foyer on level 3. Join us for the Pony Awards in Mandalay Bay, BCD, this room, at 6:30 p.m. Thank you for putting your phones on vibrate. It makes it easier for the rest of us to ignore the ringing while you wait for your voicemail to pick up. And with that, Nir and Patrick.
Good afternoon. So today we're going to speak about breaking points of interaction. It's a pretty cool title. So when we submitted our CFP, we got a response that says, are you going to bypass EMV? Are you going to bypass chip and pay? And I just want to make sure that I got it correctly. Yes, we're going to do that in this talk. We have a few demos, and you may be pretty much surprised from the findings that we have here today. So before we begin, we have a small challenge. The challenge is to introduce ourselves. Since we like to speak a lot about ourselves, we made an XML file that describes ourselves. Oh, you can't read it? I thought you can. Okay, anyway, so we just made a shorter version of ourselves, and so I'm Nir. I'm heading the application security for the NCR Corporation. I spoke at several conferences, including Black Hat, DEF CON, B-Sides, and I really like to contribute to open source stuff. That's me. I'll hand it over to Patrick.
I'm Patrick Watson. I'm an application security architect working with Nir at NCR. My job is basically to make sure that our systems are nice and secure. And I kind of think of things as if our systems, if we're not supposed to talk about how they work, then that means they're probably not secure enough. Because, well, you know, the old saying about security through obscurity. Now, this is my second talk. The first one was yesterday at B-Side, so hooray for me. First time at Black Hat. But I'm sort of on the engineering side of things. And let's talk about what our research actually is doing. So part of our job, like I said, is to make sure that our systems are secure. And that means not just the software made by NCR. It's also the whole ecosystem of the site or bank or wherever it is our software is running. So we take our software and we also analyze the devices and hardware software combinations from the other vendors at the site. Part of that is that when we're evaluating those, we took some of our software protections, turned them off, and said, okay, let's forget about our software and see how things interact with the stuff at the site. And when we did that, kind of a whole bunch of stuff popped out, and we went, oh God, what is this? This is some stuff that we didn't expect to find. Let's talk about the industry at whole a little bit first. So payments happen all over the place. Retail, hospitality, meaning restaurants or hotels, petroleum convenience stores. Taking payments at its very basic level is sort of the same everywhere, but there's little differences. And over the last few years, there's been a renewed interest in security. There were some kind of high-profile breaches you may have heard of a couple years ago in retail. And they started paying more attention to it. And what would you guys say if I told you that, well, people are paying attention to it now? We've got this security thing down. It's all fixed. We don't need the PCI standard anymore. We can just go home. Well, sort of ridiculous, right? Everybody here knows that you can't just do a point-in-time assessment of security. You have to keep going with that. So that's why we did this research.
So now that you know why we did it, let us give you some background about what are we going to attack. So when you deploy managed pin pads, meaning PIN pad that is managed by a point of sale or a payment application. Essentially, there are two general architecture types. I'd like to give you a background about the architecture types in order to explain you later how to attack these types of architecture. So the first architecture is kind of a segregator architecture. That means that you have the point of sale or a bunch of point of sales in the store. Then you have the store server. And as part of the functionality of the store server, you have a payment application. Payment application is the application that eventually communicates with a payment processor. But the thing is that you will have a PIN pad, and the PIN pad can be connected using an Ethernet cable. So if it's connected using an Ethernet cable, it may have all the IT best practices. You have a separate VLAN. Maybe it's separate VLAN in the store or separate VLAN for across the organization. Whatever it is, it's connected through Ethernet, which means that we can probably look up for the communication there, and you will see that we can do quite interesting stuff with that. And based on that, you can generate cool attacks between the payment application and the PIN pad. So essentially, we don't care about the point of sale. The next thing is actually kind of all-in-one solution, which means that you don't have Ethernet cable connected to the PIN pad. You actually have a serial port connected to the PIN pad. That makes things more difficult because although you can tap the communication, the serial communication, it's going to be a little more difficult because it's not that scalable as it should be with Ethernet, with the Ethernet connection. But it's still something that works today. So if you heard about memory scrapers like to be on these point of sales and just look up for the credit card numbers. But as I mentioned, we don't care about the point of sale. What we are trying to do here is actually to be more transparent and actually less visible by any malware detection applications. So before we go into the flows, or the flaws actually, let's talk about how payments work, because we'll go through this process several times from now on. So the components that we have are point of sale, and we have the payment application, the point of interaction, which is essentially a PIN pad that we brought here, and we have the payment processor. So the regular flow works as selling activities, which means that you add some items to your cart, and then eventually you decide to pay. So you swipe your card, it goes from the payment application to the point of interaction. The payment application requests from the point of interaction to get the credit card details. It can be track on to data if it's a swipe that you're doing on the PIN pad, or it can be EMV tags in case you're sticking your card into the PIN pad. Whatever you get it, then if it's a PIN-enabled transaction, you will also be required to enter the PIN. Again, same thing goes from the payment application back to the point of interaction and backwards. And when you've done it, then it goes to the payment processor to process the payment. If it's online, that's great. You're going to get the authorization code back. Perfect. If it's offline, well, it's quite challenging because you don't have the communication, but you still want to accept the transaction. So you store it, in most cases, in an encrypted manner on the payment application, and then you handle it later. So this is pretty much what we are doing with payment flows. The thing is that we can exploit the payment flows by just exploiting a simple thing in the authentication mechanisms to the point of interactions. So the way that we're going to attack it, as I mentioned, is focusing as putting a shim software between the payment application and the point of interaction. It can be done using a regular man-in-the-middle attack. It can be done through serial port monitoring. If obviously a software can do that, then a malware can do that as well. Or the best way to do that is actually replacing the payment application DLLs or any libraries. Because if you can replace it with your functionality, there is nothing that will identify these malware, unless you have any kind of integrity check. But the main idea here is that when a memory scraper runs, let's say that you scan an item. You scan an item, you hear the beep, right? With memory scrapers, you'll hear the beep a little bit later because it affects the performance. In this case, it will not affect the performance. You just replace the functionality, that's all. So I think that the best thing to do is start with the basic demos, and I'll hand it over to Patrick.
And Nir is going to be my cameraman for this. And while he's getting the camera set up, let me tell you a little bit about what we've got up here, because it's a little difficult for you to see this.
Hello, Black Hat.
So we've got my laptop running a point-of-sale simulator that we use for testing. It's literally just a simulator. I can push buttons that say add deli item, stuff like that. One of our payment applications that I said earlier has its security features disabled, compiled out. That way we can look at the security of the pin pad itself in isolation instead of the security of our system. So over here, we've got the pin pad itself. Because this is, we believe, a flaw in sort of the way the payment or the ecosystem is working at sites and not a characteristic of this particular pin pad, we're not divulging which manufacturer this is. We basically don't want to unfairly single them out, whereas it's not a problem just with them. Then we've got a Raspberry Pi 3 here running our attack code. The point of this is that this is kind of overkill for what we're doing. It's a very simple device. It's a simple piece of software. And you could get something even smaller than this, like a Raspberry Pi Zero that costs like $5. Stick some Ethernet connections on it, hide it somewhere at a site, and bam, you've got yourself a nice little man-in-the-middle hardware device. So let's try running a swipe transaction, see what we can pull out of this stuff. So we'll start a transaction, put a deli item on there, and try to ring up a sale. Hopefully I can get this swiper to work good. There it goes. And you can see we've already got the track data captured on the Raspberry Pi. Over here we'll complete the transaction on the pin pad.
You can take your photos, but you can't use this track number. It's a test number. Don't use it.
Yeah. If you do use it, somebody will come hunting for you. The other card we have that we'll use later is a standard test card for EMV cards. Over here, let me complete the sale. Accept the transaction. All right. So completed. Now, this is a passive man in the middle, so that's not really a surprise that you can complete the transaction and nobody's the wiser. That's fine. But let's take a look over here at what Wireshark picked up. So here you can see the interaction between the pin pad, the man in the middle, and the man in the middle in our pause simulator. For these two packets, we filtered it so you just see the ones involving the track data because nobody really cares about the rest, at least not yet. And here at the bottom of the screen, this section is where the track data can be found. And as you can see, it's just right there. There's no encryption or anything here. Now, one other important thing to know about this setup is this pin pad is running production software. You could go out to a store and just find this pin pad running this type of software in the field today. And we've made no modifications to it. The only difference that you'd see in a real store would be that they've probably prettied up the graphics a little bit. Like you might not have a solid green screen. You might have something pretty saying welcome to whatever retailer it is.
Yes. So as you can see, the communication wasn't encrypted. The idea is that we actually spoke with one of the vendors and requested them to encrypt the traffic for us. And we said, okay, can you just TLS it for us? They said, like, why? Are you sure? Well, it's a security device. You need to enable TLS 1.2. The problem is that it's more a business problem because the point of sales may be too old, so they won't be able to support the TLS 1.2. Well, actually, in several cases, you have Windows XP, so it may be difficult to implement TLS 1.2 there. And on the other hand, the pin pad may be also a little bit old. So everyone has its own justification. Let's see the demo.
Now, earlier we had talked about two different architectures for site setups. The segmented architecture where the payment server is off on its own and pin pads are connected via Ethernet, and the sort of integrated architecture where it's all in one, where the pin pads are connected to the point of sale directly, usually via serial cable. Now, one of the things I tend to hear a lot is, okay, everybody knows how to intercept packets, do a passive man in the middle, whatever, via Ethernet. That's old news. But serial cables, sometimes people are like, yeah, it's a serial cable. You have to physically intercept that to actually do anything, et cetera, et cetera. Well, not completely true. Here we've got a demo, because frankly it's kind of hard to bring multiple pin pads and you can't change configuration easily. But this is a pin pad at our office connected via serial, and we've got a serial port monitoring software from Ultima software there on the left. This is capturing the packets in real time, and here we've got highlighted the packet where we have the track data. And because this is extra small, we actually captured an image of that on the next slide that you can see here. This is, if you can tell, pretty much the exact same packet you saw earlier via Ethernet. That's important to note because it really is the same protocol via Ethernet or serial. So if you've got software that can intercept serial, they can do the exact same things that they can do via Ethernet. Now, that software you saw couldn't intercept serial port communication, obviously, because we did it, but it can also do interesting things like insert new serial datagrams and stuff. So that can kind of lead to a more active attack, which we'll talk about soon.
So we spoke about the low-hanging fruits now. Swiping data. Wow. So many people spoke about it. So many people wrote about it. That's great. We spent like 10 minutes of the time. Sorry about that. But we had to give you the background. So let's talk about the really cool stuff. How to bypass EMV. But before bypassing it, I think it's worth mentioning what EMV does and what it doesn't do. So let's talk what it does. It does prevent stealing your physical card and using it as a chip and pin transaction. So, okay, you have something you have something you know, probably you don't have the no part. Okay, that's great. That's it. That's what it does. Let's talk about what it doesn't do. EMV, let's assume that you stole a credit card number. You can capture it in the same way that we'll demonstrate in a few minutes. And you got the track data. Now, you can create a card with the same track data and pay with it in different places. Like you can pay online, you don't have chip. You can pay with manual card entry in case the card isn't working. So there are multiple ways to pay, or maybe you'll go to a store that they don't have a chip and pin supported pin pad. Also a problem. The other problem is that with the track 2 data that you have, there is a reason why sometimes you swipe the card and then the pin pad tells you, hey, sorry, you have a chip and pin card, please stick the pin inside. The reason for that is because there is a number as part of the whole track data that says this is a chip and pin card. Guess what? If you have the number, just change it to a swipe card. And then it may be approved or not. I will leave it to you. I can just say that offline modes can be very attractive. That's it. And the last scenario is actually falling back to a swipe method, which means that if you go to the cashier and let's say that you're sticking your card instead with the chip in the front, you'll just stick it with the chip in the back. The cashier will see that it doesn't work. What the cashier will do? Fall back to swipe. That's exactly what the cashier will do. And then again, you will be able to bypass EMV. So EMV is cool, but it's an old standard. It's not a secure standard. So we spoke about, or at least we mentioned that we'll be able to get the EMV data for you. Guess what? Now we're talking about the real stuff. So for the same flow that we have, for the same payment flow that we have, we just need to take one action before getting exposed to all data. First of all, get the stream software out. You're in the man in the middle. And now you're performing that transaction, obviously requesting the credit card information as the payment application requested from the point of interaction, but requested through the adversary. So the user sticks the card, the consumer sticks the card, we get the EMV data back. It's not tracked data. We won't see it as we saw it in the previous slides. But we'll need to figure out how to get the EMV tags and translate it to tracked data. Now you'll see how we do that. And eventually, once we got that, then we'll be able to proceed to the next steps. So the best thing to do is just to demonstrate it. I'm the cameraman, I know.
Will.
Yeah. Oh, here it is.
All right, so let's just start a new transaction here. Start transaction, let's add a deli item. Start the sale. We should get a prompt to insert our chip card here momentarily. There we go. Now it's going to ask us to accept the amount. Yes. And if you notice over here on the Raspberry Pi, we've already got the track data. We'll come in here and hopefully I can type the PIN correctly.
This is also a test card.
Yes. And
don't use it.
It's not a good idea to tell anybody your PIN, but since this is a test card, it's 4315. Hope I typed that right. Looks like I did. Processing approved. And it's going to ask me to remove the card. It should go back to the welcome screen momentarily. All right, transaction done. We've got the track data. Now, how did we get the track data, Nir? Because this is a EMV card, right?
Yeah, let's see that.
So here is a picture of one of the packets that you intercept from that. This is kind of obscure a little bit. You've got a section right, where's the mouse? Right here with American Express. That's because this is what's called an application identifier that says what type of card it is. Lower down, you've got this weird string right here. That's because this is a test card. Normally someone's name would appear here. This just identifies which test card you've got. Now, does anybody see track data just sitting out in the open there?
Yeah. Oh,
yeah. Well,
me.
yes.
Yeah, but I know that because I prepared the deck.
Yeah.
I wouldn't see it.
But let's give them a hint. What about now? In most payment systems, data is transferred usually using ASCII encoding. It's usually right there out in the open, assuming you're not using TLS or something. But here, it's still not quite obvious enough. But if you look over here in the actual hex representation of the binary going back and forth for EMV, this is the actual track data. And it's sort of in an odd format. They actually took the text representation of the track data and then sort of transposed it into so that you'd see the track data when you look at it in hex form. So if we transform that into readable stuff, you can see you've got the standard track format there. You've got the pan at the front, a separator, then the expiration date, that's what's in purple, then the service code, that's in sort of a orangish yellow color that sometimes doesn't show up too good, then the discretionary data. Now, let's talk about that service code. Remember how Nir was talking about you could change one character and then you could use the card offline? Well, that's what the service code is. You see the 2 at the very first, right here? That 2 means this is a chip card. If it's a 1, that means it's a swipe card. So All a attacker has to do is take that track data, change the 2 to a 1, write it to a magstripe card, and then you can use it in an offline scenario. Hosts are supposed to check that when you do an online verification, but if you're offline, nobody's the wiser.
Okay, so now we stole the track data. But we still want to purchase online. I want to get an RV, and I want a credit card for that. So we have the full name, we have the expiration date, we have the track data. What else do we need? Anyone? CVV. That's right. Well, that's a challenge. We'll probably need to bypass it. So, till now we spoke about the passive attacks. Now we'll need to do something active to get the CVV number. So our active man-in-the-middle attack is quite interesting. In this flow, we have, again, all of the components as we had before, but if you see the payment flow, we request to pay from the point of sale to payment application, then the payment application requests the credit card from the adversary and request it from the point of interaction. We get the EMV tags. Now you know that we know how to get the EMV data. And when we get the EMV tags back as the adversary, before responding to the payment application, we inject our own call to the to the PIN pad. The reason for that is because if we will inject ourselves not in this process, the transaction will just not complete successfully. But we want the consumer to feel really good with the fact that we're stealing his CVV as much as he can. So, so the way that we do that, we just call let's call it a function inside the point of interaction, and this function essentially gets us a number. We request a 4-digit number with a specific text. That's what we can do, and that's what we will demonstrate now.
So, cameraman, if you please. And I'll start up a new transaction while you're working on it. And this time, since we're getting close to lunch, I'm feeling a little hungry. Let's put on 2 deli items. We'll be daring. All right. So we've got 2 deli items. So far, same as before. Click the sale button. We'll get prompted for a EMV entry momentarily. Make sure I get it in the slot. Please wait. Now we've got the track data, same as before. Do amount confirmation. Enter the PIN. 4315. Hope I typed it right. Yep. And here's a new screen. This is our first of the attack screens. And as Nir mentioned, this is a normal built-in prompt. It's a normal prompt API. We supply the text, say, give us a card, a 4-digit number, and it'll respond back. Now, because this is a test card, it doesn't have a built-in CVV2 assigned to it, so I'm just going to enter 123. Click enter, and if you look over here, the Raspberry Pi's got it. The PIN pad finishes, approved. Should prompt remove card. There we go. Processing. And we're done. Now, let's take a look at the Wireshark and see if we actually intercepted all that. So this is all the swipe data. We'll switch to the prompt entry. So what you see right here is all the different prompt responses from the PIN pad. You see right here that this is 1, 2, 3 going from the PIN pad to the man in the middle. Here is a different type of prompt response. This is just saying that we finished a form. And here is yet another one saying, hey, we finished a different form. So as you can see, right here, PIN pad to man in the middle, that's our attack. Then man in the middle to the pause simulator, but not with the CVV. This is the data from the finished another transaction. This is the original data that we took over.
Yeah. Okay, so we've got the CVV. That's great. But we want to get more. We actually want to get the PIN, because that's a sensitive thing that we want to steal. And in fact, we can do that. So with this flow, we can actually intercept a little bit differently in the flow in such a way that allows us to get the ENV tags as previously. But now, the payment application will request the encrypted PIN. Before the adversary responds with the encrypted PIN to the payment application, we inject our own screen. And guess what this screen is going to do? Ask for the PIN. Again. Let's see that.
So, cameraman, if you please.
Yes, that's me, I know.
Let's start the transaction. Go ahead and put 2 grocery items on there this time.
Oh, you got it. Okay.
There we go. Ready?
Yeah,
all right.
ready.
Click sale. Should get the entry prompt. There it is. Insert the card. Get the track data. Now we've got the amount confirmation screen again. Yes. Trusty old enter PIN screen. This is the real one. 4315. Now, just like previously, we get a new screen. This time, re-enter PIN. Now, if you're a security professional, you may notice the difference between these two. But because we're able to put whatever text we want on this screen, we can also claim that there's a problem or whatever. And most consumers are kind of trained, if you will, to trust a PIN pad. If it's telling them to enter their PIN again, they probably assume they typed it wrong. Now, if you look at the Raspberry Pi, we've got it, unencrypted. And if we look at the PIN pad, it's approved. We get the same remove card, processing, back to welcome. So the payment application is none the wiser because the man in the middle never told it was doing that prompt. It just took over the flow of the transaction.
So let's say that we've got that. The thing is that part of the PIN pad manufacturers actually provide some protection for the text that we can inject there. So they have a whitelist. Well, guess what? We don't need to bypass the whitelist. We just need to use the whitelist. So the whitelist may include a lot of words, and it varies between the vendors. But there's one thing that is pretty much common. Please re-enter. If you've been asked to put your PIN, and then you've been asked to re-enter, what is the thing that you need to re-enter? Your PIN. But let's say that the screen may not look right, and it's not perfect. So several manufacturers actually allow you to inject screens or forms. The reason for that is because maybe on retail, as Patrick mentioned, it's pretty common, but in other business types like hospitality and petroleum convenience stores, they have their own flows. They want to customize it for their customers. And since they allow that, and it's a pretty legal stuff that they do there, we can just inject our own form. So when we inject our own form, we actually don't need to inject any text. So the enter PIN that you see here on the screen is actually a photo. We just need to add a control that gets masked number. The one limitation that the PIN pad manufacturers provide is that in some cases, you may be required to sign these forms, which may make it a little bit more difficult for the hackers to do that. So I suggest that the best thing to do is, again, demonstrate it and show it how it will work in the real-world scenario.
So, as Nir said, some manufacturers require forms or screens or whatever they call them to be signed by the manufacturer. Now, this one doesn't actually require that, which is why we're able to perform this attack. Again, production code in the field. If an attacker is smart about this, they'll do the form injection sort of ahead of time, like at 1 o'clock a.m. or something when nobody's in the store, nobody's likely to be paying attention. Because all the PIN pads actually do display something on the screen when you're doing this. It happens very quick, so we've slowed it down here, we're going to actually pause it. So watch the pin pad screen. The progress bar will be very quick on this once it actually gets going. It'll take it a second to go. So there it goes. We've got it paused after the progress bar completed, but if you noticed, there was a progress bar that advanced very, very quickly. Once it gets to this section where it says file successfully downloaded, a real attacker or real software would immediately transfer that back to the welcome screen, which, like this. Now, let's try this out using our form.
Yeah.
All right. Start transaction. Let's put a deli item and a grocery item on there this time. Do a sale. Now, just like before, it'll prompt for an EMV insert. Do that. Got the track data, as usual. Click yes to amount confirmation. Now, let's type in this PIN, 4315. Where's the 5? There it is. Hopefully I typed that right. Yep. Now, here comes our form. Now, obviously, a real attacker wouldn't do something like this. The point is that you can see that this is really a form or screen or whatever that we injected. And we also made the text of the PIN prompt a little bit different so that you can really tell that it's not the same font used in the rest of the system. So let's 4315. And as you may expect at this point, we've got the PIN over here on the Raspberry Pi as well. The PIN pad has approved the transaction. Please remove card. Processing. And we're done. Transaction approved. Now, we've shown you a few different attack vectors here, but there's probably more that we can look into, right? I mean, computer security is never actually finished with anything. So what else do we have available? Well, one of the more common things that you may have heard of are skimmers. These are old school. I'm not going to spend too much time talking about them, but we get reports of them a lot because, well, we work with these devices a lot. Some of these are incredibly advanced at this point, like the one on the far right. If it was sitting here, I would probably not be able to tell the difference between a pin pad with that overlay on it or just a regular pin pad. They're pretty advanced. Now, let's take a look at those network diagrams we were showing you before. This time we've added a diagram talking about the pin pad. And like most Internet of Things or embedded devices, people kind of tend to think of a pin pad as a single thing, as this is a nice secure device that's all in one and it's one thing. But it's really a computer like most other things. Under the scenes, it's running some applications, it's running an OS, it's got different hardware devices, stuff like that. We've only really been looking at one of those applications that runs on the pin pad. There are others on there. There's an OS on there, probably some sort of Linux variant or maybe a real-time operating system. There's also hardware devices like the secure reading and exchange of data that's basically like a TPM. It's used for the crypto operations in there. We can probably find more faults in this thing. For example, we did a form or screen insert into it, which it's accepting a big blob of data from anybody that wants to give it to it. What if there's a buffer overflow in there or something? So let's talk about some mitigations to these sort of attacks. What do we want to do?
Well, so let's split the mitigations between what a retailer can do or requests and what a consumer can do. So as for the retailers, there's something called point-to-point encryption. The idea of point-to-point encryption is to use the hardware-based encryption that you have on the pin pad to encrypt everything. Okay? Not only the pin, the whole thing. The idea is that on the pin pads, you can choose whether just to encrypt it using the hardware, the regular hardware, or you can use the TPM, which is the thread component. Preferably today, we can ask for the thread-enabled functionality, and most of the pin pad vendors will be able to provide that to you. The other thing that is important to understand is with these pin pads, you have you have encryption. Well, obviously the PIN is encrypted, but the idea is that every transaction is encrypted with different key. This is something called the DocPut algorithm. So triple DES sounds like very old thing, but triple DES DocPut means that every transaction is encrypted using a different key. This is something that you just need to verify that the PIN pad vendor will be able to provide you. One more thing that is important to understand with the point-to-point encryption in general is that we need to make sure that no one can downgrade the firmware. So sometimes you can just send a command and upgrade or downgrade the firmware of the PIN pad. If someone can use the hardware encryption and then downgrade it to software encryption, that may be problematic. Then we may be able to perform the same attacks as we did now. But if it's hardware enabled and it does not allow any downgrades, then it may be secure enough to handle with these attacks. One of the most important things in the point-to-point encryption is to make sure that if we allow any forms or screens to be uploaded or actually downloaded by the PIN pad, we need to make sure that it is signed. It's signed by the manufacturer itself or by the vendor that provides the integration with the PIN pad. In that case, you need to manage certificate authorities correctly and make sure that no one else can inject that. One of the things that we didn't manage to discuss about in this talk is the whitelist that the PIN pads manage. So you actually can have exceptions of what is going to be encrypted and what is not going to be encrypted. Think about it this way, like loyalty numbers. It's not a credit card number. It's sensitive, but it's not regulated. So in that case, you may just say, okay, I have a bin range that will be excluded. And in some cases, you don't want to leave it open for attackers just to add the Visa and MasterCard bin ranges, so that won't be encrypted at all as an exclusion. And the last time, we spoke about the offline stuff, so we need to make sure that even if you don't have the online connectivity, you still have the encrypted blob on the payment application. So this is for the customers that have some power to face with the point of interaction manufacturers. But what if they don't have the point-to-point encryption functionality? Well, you can ask them to TLS it, if they support TLS or SSL-v3. Whatever they support, you can just request it, or just work with them to sign all of your requests, and then you will be authenticated. But from the consumer's perspective, what you can do as individuals in order to avoid this attack, except obviously paying with cash. So do not ever re-enter PINs. If you see that, take your card off and restart the transaction. Don't do that anymore. Be cautious of any unusual prompts because, again, the whitelist is pretty wide. You can be asked for social security number, address, or whatever that they can ask. Just take a look at it, see if that makes sense. Like CVV2, it may be prompted in some business scenarios, but it's not something common. And the last thing is try to use kind of an app payment, or for instance, I'm paying with my watch. I'm actually, when I'm going to the grocery store, if they support paying with my Apple Watch, I will go there because I won't be prompted for all of this stuff that we saw right now. So just to sum things up, it's relatively easy to exploit the point of interactions if you're in the right place. Again, you need to be man in the middle. And there are solutions to mitigate this, these attacks. It's just a matter of requesting the right things from the manufacturer, from the PIN pad manufacturer, and from the vendor that writes the payment application for you. And I think this is pretty much what we had to say today. Thank you. And that's the time for the questions, if you have any.
We've got some microphones there,
Yes.
if you don't mind. Yeah. got about 5 minutes for questions, so try to make it quick.
Okay.
Hopefully it's on.
Hopefully it's not.
Yeah, it's on. It's on. Yeah.
Yeah, it is. So, if we have a pin pad or a whatever POI, PCI approved, let's say DuckPod, signed applications, signed firmware, signed prompts, secure element, whatever, we can assume that it's safe.
Well,
According to your scenario.
your question is, let's say that it's tested by PCI and you have all the controls that you think that you may have.
This is actually a PCI PTS certified pin pad.
It is.
And
Yes.
PCI does not require any encryption of any of the communication on a local area network at the store, which is basically where the problem comes in. So this pin pad, even though it's PTS certified by PCI, allows you to do whatever prompt you want. That's one problem. The other problem is that PCI doesn't require you to do encryption or authorization of any communication at the LAN, which is how you do the man in the middle to actually do those prompts.
And just add another comment. This is an EMV solution that should run on production.
Yeah.
And obviously it's not our production software, but we just played with the configurations or the calls that we can do on the pin pad. Okay.
Yeah.
So the idea is just to work with the two parties and make sure that they can speak in the right language.
Our
Meaning
solutions
having
actually
the security in place, not the EMV stuff, because full EMV solution, it doesn't mean that it's encrypted. It is a full EMV transaction, as you can see.
Yeah. Our solution actually uses the TLS connections or the point-to-point, one or the other, to protect against this sort of thing. But because PCI doesn't require either of those, many solutions don't do the same thing.
Any further questions? Yes. There.
For signature verification, authentication. I mean,
Can you close speaker to the mic?
as for signature verification, authentication, the point of sale terminal itself needs to have some kind of a certificate store and stuff like that. And if that deployment of certificates, is that worked out by PCI, or is it still like based on customers' whim? I mean, the retail stores' whim, whether they can deploy certificates to this. Otherwise, there's no point in having encryption. I can still do a man in the middle.
So I think, are you talking about the TLS connections?
Yes.
Okay. So PCI doesn't regulate that at all. And depending on which point of interaction it is, then some of them, when the point of sale vendor talks to the pin pad vendor, they can say, hey, point of sale or pin pad vendor, only accept connections or only create connections to this certificate because this is our certificate. Or they, by default, come with kind of the standard set of trusted root certificates, you know, the massive list that you might see in Windows or Mozilla or whatever. So our recommended approach is the vendor work with the pin pad vendor to say only trust connections to this certificate. We've got about 2 minutes, 1 minute left.
Yeah.
So,
Yes.
I was just wondering how easy it is to do a man in the middle with USB instead of serial.
Well, the question was how easy it is to do man in the middle with USB. So the idea is that you don't really need to tap in the middle. You can just replace the DLL and you're in the middle. It doesn't matter what type of communication. As long as it's I/O, you can be the man in the middle.
And most USB pin pads are actually, the USB part is just making a serial port on the computer. So it's USB, but it's just serial port over USB.
Thank you.
Welcome.
so for
Just last question? You had?
Yeah, are you planning on sharing your findings with the PCI Working Council to see if we can get changes to the PCI standards to cover that?
So Patrick is highly involved in PCI stuff, but I think we can take it offline later and talk about it.
Thank you very much.
Thank you.